Our history books are quietly becoming obsolete. A revolution is rewriting the story of ancient humanity, and it is not happening with shovels in the dirt. It is happening from the sky. The way we understand lost civilizations is undergoing a radical shift, driven not by new excavations, but by technologies that peer through dense jungle canopies and scan vast, empty deserts from orbit. This video explores how LiDAR, a laser-based terrain mapping tool, and satellite mapping, the analysis of multispectral imagery from space, are acting as a digital time machine. By the end, you will see how these tools are revealing entire lost cities and forcing us to redraw the map of the ancient world on a scale once thought impossible. We are discovering that regions we believed were empty wilderness were actually humming with complex societies. What does it mean when the ground itself holds secrets invisible for centuries? For centuries, the search for these lost worlds was a story of immense physical effort and frustrating limitations. The traditional archaeologist's toolkit was a simple one: a trowel, a brush, a notebook, and a pair of determined eyes. This method worked wonders for excavating a single temple or a royal tomb, revealing intricate carvings and precious artifacts, but it created a fundamental problem of scale. Imagine trying to understand the layout of an entire modern metropolis by only ever being able to see one city block at a time, and only after spending years carefully digging that single block out from under a forest. That was the reality. In places like the dense rainforests of Central America or Southeast Asia, visibility on the ground could be measured in mere meters. Teams would spend entire seasons cutting narrow paths through the undergrowth, a monumental task that revealed only tiny, disconnected fragments of what was really there. The result was a map of the ancient world filled with isolated dots. Archaeologists knew the locations of grand pyramids and central plazas, the obvious monumental hearts of cities. But the sprawling suburbs, the extensive farmlands, the networks of roads and canals that connected everything, these remained almost entirely invisible. It was like finding the Capitol building of a vanished nation and having no idea where its people lived, how they traveled, or how they fed themselves. The true scale of these civilizations, their population density, and their sophistication in managing the landscape was hidden, leaving a history that was monumental but curiously empty. The story was there, written not in stone but in the very shape of the land itself, waiting for a tool that could finally read it. The breakthrough came from a technology that seemed more at home in a science fiction novel. This tool is called LiDAR, which stands for Light Detection and Ranging. At its heart, it is a beautifully simple concept. Imagine a plane or a drone flying over a landscape like a dense rainforest. Instead of a camera, it carries a special laser that fires hundreds of thousands of invisible light pulses toward the ground every single second. Each pulse is a tiny messenger. When it hits something, a tree branch, a vine, a stone wall, it bounces back up to a sensor on the aircraft. The system measures with incredible precision how long that round trip took. Since we know the speed of light, that time measurement tells the system exactly how far away that object is. Do this millions upon millions of times, and you get what is called a point cloud. A massive digital swarm of individual points in three-dimensional space, each one marking the exact location of something the laser touched. But here is the true magic, the step that changes everything for archaeology. Not every pulse hits the ground. Most are caught by the dense green blanket of the canopy. But a lucky few slip through gaps in the leaves and finally strike the solid earth. Powerful computers can then filter the data. They can digitally strip away every single point that came from a plant, from the top of the canopy all the way down to the underbrush. What remains is a stunningly accurate map of the bare Earth topography, the ground itself, as if someone had reached down and pulled the entire forest away like a rug. This is the superpower of LiDAR penetration. It allows us to see the shape of the land beneath the blanket, revealing the subtle human fingerprints that have been hidden for a millennium. Gentle mounds that were once house platforms, straight lines that are ancient roadways, perfect rectangles that outline forgotten reservoirs, all of it suddenly visible in crisp, undeniable detail. It is a revelation that does not require a single cut from a machete. While LiDAR acts as a forest-stripping laser scalpel, another technology provides the wide-angle lens. Satellite mapping offers a view from the ultimate vantage point, turning entire continents into a single archaeological site. This is not about taking simple photographs from space. Modern satellites use sophisticated sensors that capture light far beyond what our eyes can see. They operate on a principle as powerful as LiDAR's penetration detection. By analyzing different wavelengths of light, both visible and invisible, these sensors can pick up on incredibly subtle clues in the landscape that are completely meaningless to a person standing right on top of them. This is called multispectral imaging. Think of it as giving the Earth a medical scan. Healthy plants reflect certain types of light, while stressed plants reflect others. A buried stone wall or a filled-in irrigation ditch will affect how much moisture is retained in the soil above it. This, in turn, affects how the plants growing there absorb light. To a satellite sensor, these minute differences in vegetation health or soil composition create distinct spectral signatures. What looks like a uniform field of wheat or a patch of scrubland to us becomes, in the satellite's data, a glowing outline of a forgotten foundation or a faint, straight line marking an ancient road. Another powerful tool is synthetic aperture radar or SAR. Instead of light, it uses microwave pulses. These longer wavelengths can penetrate dry soil and sand to a certain depth, and they are completely unaffected by cloud cover or darkness, allowing for year-round, all-weather surveying. Together, these technologies provide the sheer, breathtaking scale that complements LiDAR's precision. A single satellite pass can image thousands of square miles. This allows researchers to ask entirely new questions. Instead of wondering what is around a known temple, they can scan an entire river valley or a coastal plain to systematically look for patterns of settlement, trade routes, and agricultural systems. It makes the search for lost civilizations not just a targeted dig, but a comprehensive regional census. The ground is speaking to us in a language of light and shadow we are only just beginning to fluently understand. The real power of these tools is not just in finding new dots on the map, it is in how they connect them, fundamentally changing the very unit of archaeological study. For generations, the discipline focused on the site. This was a specific, bounded location, a city center, a ceremonial complex, a burial ground. It was a manageable piece of history you could fence off and excavate. But LiDAR and satellite imagery have shattered that containment. They force us to zoom out, to see not just the heart but the entire circulatory system of a civilization. We are no longer looking at isolated ruins. We are seeing anthropogenic landscapes, entire regions deliberately and systematically shaped by human hands over centuries. What emerges is a picture of a civilization as a complex, integrated organism. A grand pyramid is no longer just a standalone monument. Through this new lens, it becomes the central node in a vast, radiating network. The data reveals the raised causeways that connected it to outlying administrative centers. It shows the terraced farmsteads climbing the hillsides that fed its population. It traces the intricate canals and reservoirs that managed water for both agriculture and ceremony. Every home platform, every small community shrine, every defensive wall becomes part of a single, coherent system. This shift from site to landscape reveals the true genius of these societies. It was not merely their ability to build massive structures, but their profound understanding of engineering and ecology on a regional scale. They did not just build in their environment, they engineered it, molding valleys and forests into a sustained, productive home for millions. The empty spaces between the known ruins, once considered mere wilderness, are now understood as the essential connective tissue, the farmlands, roads, and waterways that made the monumental centers possible. This transforms our understanding from a collection of spectacular artifacts to the living, breathing pattern of an entire society. The dense jungles of Guatemala and Belize held their secrets tightly for over 1,000 years. Then, in 2009, a LiDAR-equipped plane flew over the ancient Maya city of Caracol. What came back was not just a map, it was a revelation. The data digitally peeled back the rainforest to reveal a metropolis of staggering scale and sophistication. Caracol was not a collection of a few temples in a clearing. It was a vast, interconnected urban landscape. The LiDAR map showed a dense patchwork of over 100,000 individual structures, from grand palaces to modest household platforms, all woven together by a complex network of raised causeways. These were not simple paths, but engineered highways that connected the city center to distant agricultural terraces and residential districts. The survey also revealed an intricate, city-wide water management system of reservoirs and canals, proving the Maya engineered their environment with precise, deliberate control. This single survey multiplied the known size of Caracol many times over, forcing a complete reassessment of its population and power. It showed a city designed not just for ceremony, but for living, a true urban center thriving within the rainforest. But Caracol was only the beginning, a preview of a much larger story waiting to be told. The real seismic shift came from broader surveys in the Guatemalan region known as the Mirador Basin. Here, LiDAR unveiled something that fundamentally rewrites Maya history. The jungle canopy had been hiding not just cities, but a continuous, interconnected urban fabric. The scans revealed over 60,000 previously unknown structures, including pyramids, fortifications, and thousands of kilometers of causeways linking major centers. This was not a landscape of isolated city-states occasionally at war, as was long believed. This was a vast, integrated network, a pre-industrial megalopolis. The scale of landscape modification was breathtaking. Vast areas of wetland were drained and converted to farmland. Hillsides were sculpted into terraces, and the road systems indicate a level of political and economic cooperation across great distances that scholars never suspected. The most stunning conclusion is demographic. Based on this new data, researchers now estimate the classic Maya population could have been in the tens of millions, far higher than previous conservative guesses. This paints a picture of a civilization that achieved a staggering scale of complexity, managing their tropical environment with an intensity that rivals modern agricultural practices. The empty, mysterious jungle of popular imagination vanishes, replaced by the image of a managed, bustling, and profoundly connected world. This same technological lens has turned its gaze to the other side of the world, to the humid plains of Southeast Asia. Here, the story of the mighty Khmer Empire and its legendary capital, Angkor, is being rewritten not by finding new temples, but by finally seeing the spaces between them. For generations, the awe-inspiring temple of Angkor Wat stood as the symbolic heart of the empire, a masterpiece of stone and spirituality. But the true genius of the Khmer was not just in their monuments, it was in their mastery of water. And for centuries, the full scale of that mastery remained hidden beneath rice paddies and secondary forest. Recent LiDAR and satellite surveys have now digitally reconstructed the ancient landscape, revealing that the city of Angkor was not a compact urban core. It was something far more revolutionary, a vast, low-density urban complex that sprawled over an astonishing 1,000 square kilometers. this was not a city in the traditional, crowded sense. It was a meticulously planned, engineered landscape where residential districts, local temples, and village ponds were distributed across a wide area, all integrated into a single, gargantuan system. The defining feature of this system, now visible in stunning clarity from above, was water. The data maps an intricate, grid-like network of canals, channels, and embankments that look less like ancient infrastructure and more like the circulatory system of a living being. At the heart of this network were the massive reservoirs known as barrays. These were not simple ponds, they were colossal feats of engineering, artificial lakes spanning kilometers, designed to capture and store monsoon rainwater. The canals distributed this life-giving resource across the urban expanse for agriculture, sanitation, and ceremony, but the system was also about control. A sophisticated network of embankments and spillways managed flooding during the intense rainy season and released water during the dry months, stabilizing the environment and allowing for multiple rice harvests each year. This hydraulic city reveals an empire that did not just adapt to its environment, it completely re-engineered it on a geographic scale that is difficult to comprehend. The temples were the spiritual pinnacle of this society, but this newly revealed web of waterways was its foundational genius, the practical engine that sustained a population of perhaps 1 million people in what was once considered an inhospitable jungle. The stones of Angkor Wat tell a story of devotion, but the shape of the land now tells the far grander story of survival, sustainability, and breathtaking hydrological foresight. The story of human ingenuity in the Americas grows even more profound as we journey from the engineered landscapes of the Maya and Khmer to a place long considered the ultimate, untouched wilderness. For generations, the vast Amazon rainforest was portrayed not as a cradle of civilization, but as its opposite. The dominant narrative, supported by early archaeological work, suggested this immense green world was a pristine environment, only sparsely populated by small, nomadic tribes who lived lightly upon the land, leaving no permanent mark. This view shaped our understanding of the continent's history, suggesting that large, complex societies were only possible in the highlands of the Andes or the arid coasts of Peru. But that story, like the forest canopy itself, has now been lifted away. The latest LiDAR surveys are revealing a truth that turns centuries of assumption on its head. The Amazon was not a virgin wilderness waiting to be discovered. It was a homeland, a garden, and in many places a city. Flying over regions in Bolivia and Brazil, laser pulses are mapping the ground to reveal stunning geometric patterns etched into the earth. There are perfect circles, squares, and octagons formed by ditches and embankments. There are clusters of raised platform mounds arranged around central plazas, the clear footprints of planned settlements. Most astonishing are the extensive, straight causeways that stretch for kilometers, connecting these sites into a regional network. These are not the random trails of hunter-gatherers. These are the signatures of settled, organized societies that lived here for generations, societies that deliberately and systematically sculpted their world. The scale of this modification is what shatters the old paradigm. The evidence points to a form of sophisticated agroforestry, where these communities did not simply take from the jungle, but actively cultivated it. They enriched the naturally poor Amazonian soil by creating what scientists call terra preta, or dark earth, a fertile, human-made soil packed with charcoal and organic matter. This allowed them to support larger, permanent populations. What we are seeing is not evidence of a civilization that fought against the rainforest, but one that worked with it in a profound partnership, cultivating useful trees and plants within a managed park-like landscape. These were garden cities blending settlement, ceremony, and agriculture into a single, sustainable system. This discovery does more than add new dots to a map. It forces a complete rethinking of the carrying capacity of the Amazon and the cultural achievements of its people. It suggests that when European explorers first gazed upon this green ocean, they were not looking at untouched nature. They were likely looking at the overgrown gardens of a once thriving world, a world that had already passed, its grand earthworks slowly being reclaimed by the very forest it had learned to nurture. The wilderness, it turns out, was a carefully tended home. But this transformation in our understanding is not confined to the world's jungles. The same technologies that peer through foliage are now illuminating the opposite extreme, the vast, open expanses of the desert. In these arid landscapes, the challenge was never a concealing canopy, but an erasing force, wind and sand that can bury entire cities in a slow, relentless tide. For centuries, the shifting dunes of the Sahara or the stony plains of the Arabian Peninsula seemed to hold nothing but emptiness, their secrets locked beneath a dry, featureless surface. Yet here, the unique capabilities of satellite mapping come into their own, acting as a kind of X-ray vision for the sands. While LiDAR's lasers excel at mapping surface topography, satellites armed with synthetic aperture radar and infrared sensors possess a different superpower. They can detect what lies beneath. Radar's microwave pulses can penetrate dry, sandy soil to reveal buried structures, like the foundations of walls or the outlines of ancient riverbeds now long dry. Even more subtly, infrared sensors can read the thermal and moisture properties of the Earth. A buried stone wall or a compacted ancient roadway retains and releases heat differently than the loose sand around it. Similarly, the ghost of a filled-in well or an underground irrigation channel can create a faint signature of slightly higher moisture in the soil, a signature completely invisible to the human eye but glaringly obvious to a satellite's spectral eye. This allows researchers to see not just what is on the surface, but the lingering imprint of what was. In the deserts of Arabia, this technology has helped trace the lost incense routes of the Nabateans, the builders of Petra. By identifying subtle linear features and patterns, satellites have pinpointed the locations of remote caravanserais, the ancient roadside inns where trade caravans would rest. These way stations were the vital lifelines of the economy, and finding them allows us to map the entire skeletal system of trade that connected continents, revealing how goods, ideas, and cultures flowed across what we mistakenly saw as barren wasteland. Similarly, in the Sahara, vast areas that appear utterly lifeless on modern maps are now showing the spectral outlines of lost lakes and river networks from a greener past. Along these paleo shorelines, satellite imagery has detected the circular patterns of ancient livestock enclosures and the faint grids of settlements, telling a story of a time when pastoral communities thrived in a landscape that is now profoundly different. Even in the high, cold deserts of the Gobi, these tools are identifying the remnants of the Silk Road's northern branches, finding forgotten outposts and watchtowers that guarded the flow of silk and spices. Each of these discoveries does more than add a pin to a historical map. It rewrites the narrative of these regions from places of isolation and hardship to central chapters in the story of human connection and adaptation. The desert, we are learning, was not a barrier but a corridor, its emptiness an illusion crafted by time and shifting sands. The civilizations that flourished there mastered their environment with an ingenuity that left a permanent, if hidden, signature on the land, a signature we can now finally read from the silence of space. Yet the past is not only hidden beneath jungle or sand, it lies directly beneath our feet. The greatest challenge for modern archaeology may not be a remote wilderness but the bustling, paved-over heart of a living city. Here, the layers of history are compressed into an urban palimpsest, a manuscript where the ink of one era has been written over the text of another, again and again. Excavating in these spaces is often impossible, blocked by subway tunnels, modern foundations, and the sheer density of contemporary life. But the same suite of technologies is now allowing us to read this overwritten text without turning a single shovel of earth. In places like London, a city built upon its own ancient ruins, ground-penetrating radar has become the essential tool. Unlike LiDAR, which maps from above, ground-penetrating radar is used from the surface. It sends pulses of radio waves into the ground, which bounce back when they encounter changes in density, like the interface between soil and stone. Walking this equipment across a modern park or a city square, researchers can map the outlines of Roman villas, medieval market stalls, and lost rivers that now flow through pipes deep underground. They can trace the ghostly footprint of a long-demolished city wall, its stones still resting where they fell centuries ago, all while commuters walk unknowingly above. In other historic European cities, aerial LiDAR mounted on drones is being used to create ultra-precise three-dimensional models of standing structures. By analyzing the minute variations in the surface of a cathedral or a castle wall, the technology can detect where older masonry has been incorporated into newer construction, revealing phases of building and destruction that are invisible to the naked eye. Perhaps most powerfully, these non-invasive methods are being applied in modern metropolises across Asia, Africa, and the Americas, cities that grew atop pre-colonial settlements. Here, the work is not just about curiosity, it is about cultural reclamation and urban planning. Mapping the subsurface remains of ancestral structures allows communities to honor that history, sometimes guiding new construction to avoid sacred or significant sites. This technological layer peeling transforms a modern street grid into a living timeline. It reminds us that our contemporary world is not a clean break from the past, but the latest sentence written on a very old page. The city you walk through today is not one place but many, all occupying the same coordinates in space, separated only by time, and now by the penetrating gaze of a radar pulse. But the raw data from a LiDAR flight or a satellite pass is not yet a map of a lost city. It is a digital blizzard. Each one of those millions of laser returns is a single point of light floating in a vast three-dimensional void. The true magic, the act of digital archaeology, happens next in the quiet space of a computer lab. This is where specialists transform that chaotic point cloud into a legible story. The first step is a process called classification. Powerful algorithms guided by human expertise begin to sort the points into categories. They identify the dense clusters that represent the forest canopy. They separate out the lower vegetation, the underbrush and vines, and they isolate the most precious points of all, the ones that made it all the way down to strike the bare earth. This filtering is meticulous, like panning for digital gold, sifting through noise to find the clear signal of the ground itself. Once these ground points are isolated, they are used to construct a highly detailed digital elevation model, or DEM. Think of this as the ultimate contour map, a precise, three-dimensional representation of the Earth's surface with every hill, valley, and subtle depression rendered in exacting detail. It is a landscape stripped bare, waiting to be read. Now the real detective work begins. An archaeologist, trained to recognize the human signature in topography, sits before this pristine digital model. They are not digging with a trowel, but excavating with their eyes and intuition. They scan the surface, looking for patterns that nature does not make. A perfectly symmetrical mound rising from the flat terrain becomes a potential pyramid platform. A series of low, linear ridges in a straight line reveals the ghost of a road or a defensive wall. A sharp, geometric depression, often aligned with the flow of water, outlines an ancient reservoir or canal. What appears as random bumps and textures to an untrained eye resolves, for the specialist, into the clear layout of a neighborhood, a ceremonial plaza, or a network of agricultural terraces. This is a form of remote excavation. They can measure the dimensions of a structure, calculate the volume of an earthwork, and trace the connections between features across miles, all without ever disturbing the soil. It allows for a profound planning advantage. By digitally identifying the most promising locations, like a cluster of house platforms or a unique ceremonial structure, field teams can then travel to that exact spot with a clear purpose, maximizing their time and preserving the site by minimizing unnecessary digging. The map becomes the first draft of history, written not in ink but in the subtle, enduring shape of the land. This digital map is far more than a picture. It is a database, a rich numerical archive of a lost world. With this data, archaeology is undergoing a quiet but profound revolution, transforming from a discipline of descriptive storytelling into a rigorous, data-driven social science. The subtle contours of a LiDAR map or the spectral patterns in a satellite image can now be translated into hard numbers that tell us not just what was there, but how it functioned. For the first time, we can quantify the unseen. Take the simple question of scale. Before, an archaeologist might describe a pyramid as large or impressive. Now they can calculate its precise volume in cubic meters, down to the last basket of earth moved. By analyzing the dimensions of residential platforms across a scanned landscape, they can generate sophisticated estimates of population density for an entire region, not just a single city center. This allows them to model how many people a given area could support, its carrying capacity by mapping the extent of terraced fields, canal-irrigated zones, and managed forest gardens. The data reveals the agricultural engine that powered the civilization. Furthermore, Geographic Information Systems, or GIS software, turns ancient infrastructure into a living network. Researchers can input the newly discovered causeways and roads into these systems. The software can then calculate travel times between settlements, analyze the efficiency of the transportation grid, and even model the flow of resources like water or trade goods across the landscape. This moves us beyond guessing about connections to understanding the logistical and economic pressures that shaped a society. We are no longer just interpreting artifacts, we are running simulations on the past. This quantitative shift forces us to ask new, more precise questions. Instead of wondering if a society was complex, we can ask how complex. What was the total labor investment in their infrastructure? How did their settlement patterns optimize access to water and farmland? The answers, derived from millions of data points, provide a startlingly clear and objective foundation for understanding the true scale of human achievement. The story of these lost civilizations is no longer written only in poetry, but in the compelling, undeniable language of mathematics. Perhaps the most profound impact of this new vision is not what it reveals, but what it redefines. For decades, our historical vocabulary has been dominated by a single, dramatic word: collapse. The classic Maya collapse, the Khmer collapse, the fall of empires. It conjures images of sudden catastrophe, of silent, empty cities reclaimed by the jungle, of entire civilizations simply vanishing. This narrative is clean, compelling, and according to the new data, largely incomplete. The maps created by LiDAR and satellites are forcing a fundamental reassessment of what we mean when we say a society ended. The story is not one of abrupt disappearance, but of profound transformation. Take the Maya. The traditional tale tells of a catastrophic collapse around the year 900, when the great ceremonial centers were abandoned and the rainforest swallowed the cities whole. Yet the laser maps tell a more nuanced story. In regions around Caracol and elsewhere, the data reveals evidence of continuous, smaller-scale occupation long after the grand temples ceased to be the focal points of power. What looks like abandonment from the perspective of a pyramid is actually a shift in how people lived. The sprawling, integrated urban networks visible in the Mirador Basin may have decentralized. Populations likely migrated, not vanished. They moved to new areas, adapted their agricultural practices, and reorganized their communities into smaller, more resilient units. The political superstructure of kings and monumental construction projects may have dissolved, but the people, their culture, and their knowledge persisted. This pattern is not unique. In Cambodia, the story of Angkor's end has often been framed as a sudden abandonment after a Thai invasion or an ecological crisis. Yet detailed landscape analysis suggests a longer, more complex process. The vast hydraulic system, a marvel of engineering, may have ultimately become its own vulnerability. Maintaining those massive canals and reservoirs against siltation and shifting climate patterns would have required immense centralized labor. As pressures mounted, the system may have gradually fragmented. People likely moved out of the low-density urban sprawl and toward the Mekong River or other waterways, re-centralizing in different patterns. The civilization did not end, it transformed, its people adapting their lives to new environmental and political realities. This forces a crucial refinement of our historical models. The idea of a clean, catastrophic collapse is being replaced by a messier, more human story of resilience, decentralization, and cultural continuity. Societies are not light switches that flip on and off. They are complex systems that change, adapt, and sometimes reconfigure themselves in ways that leave their grandest architecture behind. The silence we perceived in the jungle was not the silence of extinction, but the quiet hum of a society that had chosen a different path, a path whose footprints we can now finally see etched into the very earth they once called home. The story of these lost worlds is no longer locked away in expensive, classified satellite feeds or the exclusive domain of well-funded university expeditions. A quiet revolution in access is underway, one that is fundamentally democratizing the very process of discovery. For the first time in history, the tools to search for lost civilizations are becoming available to virtually anyone with an internet connection. Companies like Planet Labs operate constellations of small, shoebox-sized satellites that image the entire Earth's landmass every single day. This torrent of daily data is increasingly accessible for commercial and educational use. At the same time, powerful geographic information system software, once a costly specialist tool, now has robust, free, open-source versions available for download. This combination is shattering the old model. The search is moving from the exclusive helicopter flyover to the collaborative online platform. This shift is embodied by projects like Global Explorer. Founded by archaeologist Sarah Parcak, a pioneer in satellite archaeology, the platform presents volunteers with small, anonymized tiles of satellite imagery. Through a simple tutorial, anyone can learn to scan these images for the telltale signs of human activity, like unusual geometric shapes, straight lines, or distinctive soil discolorations that might signal a buried structure. When multiple users flag the same potential feature, it rises to the top for expert review. This is not a game, it is genuine, crowdsourced research. In its first initiative in Peru, volunteers analyzed over 150,000 satellite images, identifying thousands of potential new archaeological sites, including a likely lost settlement in the Andes. This model leverages a powerful truth. There are more curious eyes in the world than there are professional archaeologists. By distributing the task of initial scanning, it allows experts to focus their ground-truthing efforts on the most promising leads, dramatically accelerating the pace of discovery. The implications of this democratization run deep. It transforms archaeology from a distant, academic pursuit into a shared, global endeavor. A student in Mumbai, a retiree in Oslo, and a teacher in Buenos Aires can all contribute to finding a lost city in the Amazon or a forgotten fortress in the Middle East. This inclusivity fosters a broader sense of stewardship and connection to our shared human heritage. It also brings a diversity of perspective to the search itself. Different cultural backgrounds and ways of seeing can sometimes spot patterns that others might miss. Furthermore, this open-source approach empowers local communities and researchers in countries with rich archaeological records but limited funding. They can access the same satellite imagery and analytical tools as major international institutions, enabling them to lead the research into their own history. The dynamic is no longer one of external experts arriving with all the answers, but of collaborative partnership where technology provides a common map and many hands help to read it. The quest to understand our past is becoming a conversation, open to all who wish to listen and contribute. Yet this incredible power to see the unseen comes with profound responsibility. Every newly revealed map of a lost city is not just a scientific triumph, it is a cultural treasure, and its precise coordinates are a potential vulnerability. The same satellite imagery that guides researchers can, in the wrong hands, become a shopping list for looters. This is the dual edge of the technological blade. For centuries, the remoteness of many sites provided a layer of protection. Now, a publicly available satellite photo can point directly to an unguarded mound rich with artifacts. The illegal antiquities trade is a global problem, and the erosion of a site by looters' pits is a permanent loss of context, destroying the story an object could tell about the society that created it. This reality forces a crucial ethical conversation that must be part of the modern archaeologist's toolkit, a conversation about stewardship, consent, and respect. The guiding principle is shifting from one of discovery for its own sake to one of collaboration. Increasingly, projects begin not with a laser scan from the sky, but with dialogue on the ground. This means engaging with indigenous communities and local descendants for whom these places are not lost at all, but part of a living heritage. Their traditional knowledge is an invaluable layer of data, offering insights into the purpose of a structure or the meaning of a landscape feature that no sensor can detect. More importantly, these communities have a fundamental right to decide how, or even if, their ancestral sites are studied and shared. This collaboration extends to the handling of sensitive information. Many research teams now practice selective transparency. They may publish their overarching findings and broad maps while withholding the exact geographical coordinates of vulnerable sites from public databases. They work closely with local heritage authorities to secure and monitor locations, using the technology not just to find, but to protect. The ethical use of these tools also requires deep cultural sensitivity. A LiDAR map might reveal the layout of a burial ground or a ceremonial space considered sacred. Broadcasting those details could be deeply disrespectful, violating spiritual traditions. Responsible researchers navigate this by following community guidance on what can be mapped, what can be published, and how the knowledge should be presented. This reframes the entire endeavor. The goal is no longer simply to unveil secrets hidden from the world, but to assist communities in reconnecting with and safeguarding their own history. It transforms the archaeologist's role from that of an external explorer to a supportive partner. The true measure of this technological revolution, then, will not be counted in the number of cities found, but in the care with which we listen to the voices of the present as we learn to see the footprints of the past. Yet for all their power, these tools see only in black and white. They map the physical skeleton of a lost world, but they cannot tell us the color of its life. A LiDAR point cloud reveals the perfect geometry of a pyramid platform, but it remains silent on when it was built, what ceremonies were performed atop it, or what the people who gathered there believed. This is the crucial, humbling limitation of the view from above. The technologies are extraordinary at answering the question of where and what shape. They are almost powerless to answer the questions of when, how, and most importantly, why. They provide the map but not the story written upon it. Consider a simple linear feature cutting across the digital landscape. From a satellite, it could be an ancient road, a defensive wall, a ceremonial pathway, or an irrigation canal. The form is clear, but the function is a mystery. Only by visiting that precise location, by examining the soil layers and construction techniques on the ground, can an archaeologist begin to interpret its purpose. Even more fundamentally, these remote methods cannot provide a date. A stunning city layout visible in a LiDAR scan could be 2,000 years old or 500. There is no timestamp in the laser return. Establishing a chronology still depends on the traditional, painstaking work of excavation, finding pieces of pottery, samples of charcoal, or other materials that can be subjected to scientific dating methods. Without this, we have a breathtaking snapshot utterly disconnected from time, a city without a century. Furthermore, the rich texture of daily life remains invisible. The satellite sees the outline of a residential compound, but it cannot show the clay pot used for cooking, the stone tool for weaving, the figurine used in a household ritual, or the seeds that tell us what people ate. This material culture, the artifacts of everyday existence, is the voice of the ordinary person. It speaks to social hierarchies, economic networks, family structure, and spiritual practices. A laser pulse striking a mound knows nothing of the artisan who carved a jade pendant buried within it. These tools, for all their scale, are blind to the individual. They reveal the grand patterns of society, the highways and reservoirs, but they miss the fingerprints on the pottery and the wear on the doorstep. This is why the most advanced satellite survey always points back to the Earth. The technology guides the trowel. It tells the field team exactly where to dig, maximizing their chance of success and minimizing disturbance to the site. But it does not replace the careful brush, the meticulous note-taking, or the respectful collaboration with local communities whose oral histories can provide context no sensor ever will. The view from space gives us the blueprint. The work on the ground writes the biography. One shows us the scale of human achievement, the other reveals its heart and soul. While the spectral eyes of optical satellites are blocked by a simple cloud, another technology listens to the Earth with a different kind of vision. Synthetic aperture radar, or SAR, does not use light at all. It sends out pulses of microwave energy, the same kind of radiation used in a kitchen microwave oven, though at vastly lower power. These longer wavelengths possess two superpowers crucial for archaeology. First, they are virtually unimpeded by weather. Clouds, rain, smoke, even the darkness of night are completely transparent to radar. This allows for consistent, year-round monitoring of a region, capturing data regardless of the season. Second, and more astonishingly, these microwaves can penetrate. They can pass through certain materials that stop light cold. In a dense rainforest, while LiDAR's laser pulses are mostly caught by the top of the canopy, SAR's microwaves can penetrate the leafy layers and interact with the larger branches and the ground below. But their most dramatic application is in the world's dry places. In arid deserts with loose, dry sand or soil, the microwave pulses can actually penetrate the surface layer, sometimes by several meters, and bounce off buried structures or harder layers beneath. It is a form of remote sensing that acts like an X-ray for the landscape, revealing what lies hidden not under foliage, but under the very ground. This makes SAR an indispensable tool for finding features that have been completely erased from surface view. A powerful example is the search for lost waterways. Across the Sahara and the Arabian Peninsula, researchers use SAR data to detect paleochannels, the ghostly outlines of ancient rivers and streams that flowed during wetter climatic periods thousands of years ago. These channels are now filled with sand, invisible to the naked eye and often undetectable to other satellite sensors. But the buried sediment retains slightly more moisture than the surrounding desert, or has a different density. When the radar pulse hits this subsurface feature, it returns a slightly different signal. Processed into an image, these long, winding paleochannels glow like faint scars across the digital map. This discovery is transformative because water is the ultimate attractor. Finding these lost rivers immediately tells archaeologists where to look for evidence of human settlement. It is along these vanished banks that hunter-gatherers would have camped, pastoralists would have watered their herds, and early trading communities would have established routes. The SAR data does not find the cities directly. It finds the reason the cities would have existed in the first place, drawing a map of opportunity across a landscape that now appears utterly barren. Similarly, in the jungles of Mesoamerica, SAR complements LiDAR by helping to distinguish natural features from human-made ones. Its ability to penetrate canopy and provide information on surface roughness and moisture helps confirm the artificial nature of a long, straight causeway or the geometric shape of a plaza, building a more robust case before a team ever sets foot in the forest. This technology reminds us that the past is not always buried deep. Sometimes it is just beneath our feet, waiting for the right wavelength of energy to whisper its story back to us. These digital maps do more than reveal the past, they document its precarious present. By comparing satellite images taken over decades, archaeologists are creating a heartbreaking time lapse of history in reverse. A single pass shows a snapshot, but repeated observations year after year transform that snapshot into a moving picture, one that reveals not construction but erosion. This temporal analysis provides a sobering, undeniable record of how quickly our shared heritage is vanishing. The causes are varied and relentless. On the outskirts of growing cities, the geometric grids of modern suburbs can be seen slowly encroaching upon the faint, circular outlines of ancient settlements visible in earlier imagery. In regions of intensive agriculture, deep plowing for new fields gradually scours away the subtle surface traces of ancient earthworks, flattening history into fertile soil. The scars of looting are particularly stark. What was once a smooth, unbroken mound in a 1970s spy satellite photo may, by the 2000s, be pockmarked with dozens of dark pits, the telltale signs of illegal digging that shatters archaeological context forever. Perhaps most insidiously, climate change acts as a silent accelerant. Rising sea levels threaten coastal sites, while increasing drought and desertification expose delicate ruins to greater wind erosion. In permafrost regions, thawing ground destabilizes structures preserved for millennia in ice. This longitudinal view from space provides a powerful, objective tool for conservation. It allows heritage organizations to quantify the rate of damage, to prioritize the most threatened sites for protection, and to advocate for their preservation with hard, visual evidence. The time-lapse does not just show loss, it measures it, turning a vague concern into a data-driven crisis. Watching a known archaeological feature shrink or fragment over a 20-year span is a visceral experience. It frames heritage not as a static relic, but as a living, vulnerable landscape in a race against time. This application of the technology shifts the mission from pure discovery to urgent stewardship, using the view from above not to find what was lost, but to protect what little remains. The sheer volume of data now available is itself a new kind of wilderness. We have moved from a scarcity of information to a flood of it, with satellite archives holding petabytes of imagery and LiDAR surveys generating billions of data points for a single region. For a human researcher, manually scanning every pixel of this digital landscape is an impossible task, like trying to count every grain of sand on a beach with a magnifying glass. This is where the next frontier emerges, not in the sensors themselves, but in how we interpret their output. The key lies in teaching machines to see what we see, to recognize the human signature in the chaos. This is the role of artificial intelligence and machine learning, acting as a force multiplier for human curiosity. These are not sentient robots plotting excavation sites, but sophisticated algorithms trained to perform one task with superhuman speed and consistency: pattern recognition. The process begins with teaching. Archaeologists feed the AI a curated set of training data, thousands of labeled examples. They show it what a Maya house platform looks like in a LiDAR elevation model, highlighting its distinctive rectangular shape and raised profile. They show it the straight, linear signature of an ancient Roman road in a satellite image, or the circular depression of a storage pit. The algorithm analyzes these examples, learning to identify the complex combination of visual features that define each type of archaeological feature. It learns to distinguish a natural hill from a ceremonial mound, an old riverbank from a constructed causeway. Once trained, this digital assistant can be set loose on vast, uncharted datasets. It can analyze 10,000 square kilometers of satellite imagery in the time it takes a team to review a single county. It scans systematically without fatigue, flagging every anomaly that matches the patterns it has learned. This does not replace the archaeologist, it empowers them. Instead of spending months staring at screens, the researcher receives a curated map of high-probability targets. The AI says, here, in these 500 locations across this valley, the data suggests there is something built by human hands. This allows the human expert to bring their intuition, context, and deeper understanding to a manageable set of possibilities, dramatically accelerating the discovery pipeline. We are moving from a model of manual search to one of intelligent triage. The machine handles the brute force scanning of a continent, while the human focuses on the nuanced interpretation of a community. It is a partnership that respects the scale of the data and the irreplaceable value of human insight, turning an overwhelming ocean of information into a navigable map of our past. This collaborative fusion is birthing an entirely new discipline, a field where the trowel meets the algorithm. The modern archaeologist is no longer a solitary figure in a trench, but the conductor of a digital orchestra, bringing together specialists whose languages were once worlds apart. They now sit alongside remote sensing scientists who understand the physics of laser scattering, with data analysts who can write code to filter noise from a billion-point cloud, and with software developers who build the custom tools to visualize ancient landscapes in 3 dimensions. This is not a simple handoff of data, it is a deep, ongoing conversation. The archaeologist explains what a ceremonial causeway might look like in elevation data, and the data scientist trains a machine learning model to search for similar patterns across 10,000 square miles. The software developer then creates an interactive map that allows the archaeologist to virtually walk that discovered causeway, measuring its width and slope from their desk. This interdisciplinary loop accelerates discovery in ways previously unimaginable, turning a question into a query and a hypothesis into a map. But the collaboration stretches even further, reaching into the realm of climate science. To understand why a civilization transformed or a city was abandoned, archaeologists now partner with paleoclimatologists who study ancient climate proxies like ice cores and sediment layers. By combining the precise timeline of a site's occupation from excavation with climate models of historical drought cycles or rainfall patterns, they can ask profound new questions. Did a prolonged drought strain the massive water management system at Angkor? How did shifting monsoon patterns influence settlement in the Indus Valley? This fusion allows them to move beyond speculation about environmental stress and toward modeled scenarios, examining the resilience of ancient societies in the face of climatic change. The result is a richer, more nuanced history that sees human civilizations not as isolated entities, but as dynamic participants in a changing planetary system. The digital archaeologist is therefore a new kind of synthesist, a translator between the language of the soil and the language of the server, weaving together threads from geology, computer science, ecology, and history to reconstruct the full, vibrant tapestry of the past. The map of our ancient past is being redrawn before our eyes. This is not a minor update or a footnote correction. The cumulative weight of evidence from LiDAR and satellite mapping is demanding a fundamental rewrite of our history textbooks. For generations, these textbooks presented a specific narrative. They focused on a handful of well-known cradles of civilization, like Mesopotamia, the Indus Valley, and the Nile. Beyond these bright spots, the maps often faded into vast, blank spaces labeled as wilderness, frontiers, or lands of nomadic tribes. The story was one of isolated brilliance in a largely empty world. That story is now obsolete. The new data reveals that many of those blank spaces were not empty at all. They were home. The Amazon basin, the dense jungles of Central America, the deserts of Arabia, these were not marginal backwaters. They were the very heartlands of sophisticated, innovative societies that managed their environments on a colossal scale. We are not simply adding a few more dots to the old map. We are discovering that the dots were always there, and they were so numerous and so closely connected that they form a continuous, vibrant fabric. This points toward a revolutionary conclusion. The ancient world was far more densely populated, far more interconnected, and far more creatively adapted to its diverse environments than we ever dared to model. Our traditional estimates of pre-industrial populations are likely far too low. The empty wilderness that framed our historical imagination is vanishing, replaced by a panorama of human activity. This changes everything. It reshapes our understanding of cultural development, suggesting that complexity and innovation arose not in a few privileged river valleys, but repeatedly in parallel across continents. It redefines what we consider a successful civilization, moving the focus from monumental stone cities to equally sophisticated landscapes of earth, water, and managed forest. The narrative shifts from one of a few great cultures surrounded by emptiness to a world humming with a diversity of complex societies, many of which thrived for centuries in places we once thought impossible. This is not just new archaeology, it is a new chapter in the human story, one that finally gives voice to the millions who lived, built, and shaped our planet in ways we are only beginning to comprehend. But the technological horizon stretches even further, promising a future where our digital time machine gains both microscopic precision and planetary scope. The next leap is already taking flight on the wings of drones. While aircraft-mounted LiDAR gave us the first breathtaking view beneath the canopy, drone-mounted systems are bringing the focus down to the centimeter. Imagine a small, quiet drone hovering just above a cleared archaeological site. Its laser scanning not just the ground, but every stone, every fragment of a fallen wall in staggering detail. This is ultra-high-resolution mapping, creating three-dimensional models so precise they can record the individual tool marks on a carved stela or the subtle wear patterns on an ancient staircase. It allows for virtual preservation, a perfect digital twin of a site that can be studied long after erosion or time has altered the original. This resolution bridges the gap between the landscape view from space and the intimate details of the trowel's work. Beyond drones, laboratory science hints at even more sensitive tools. Researchers are exploring the potential of quantum sensing. This technology, still in its early stages, uses the strange properties of quantum mechanics to detect minuscule changes in magnetic or gravitational fields. The theory is that large subsurface structures, like buried foundations or tombs, create tiny disturbances in the Earth's natural fields. A future quantum sensor, perhaps carried by a drone or a satellite, could map these disturbances, effectively allowing us to see deep underground without any digging at all, revealing entire buried city layouts invisible to every other technology. Meanwhile, the view from space is about to get exponentially sharper. A new generation of private satellite constellations is launching, promising not just daily global coverage, but imagery with resolution so fine you could distinguish individual stones from orbit. We are approaching an era where an archaeologist could, from their desk, zoom in on a remote patch of desert or forest and visually identify potential structures with a clarity once only possible from a low-flying plane. This convergence of tools points toward a staggering possibility: the comprehensive archaeological mapping of entire continents. The dream is a true, living atlas of human history, a dynamic digital layer over our planet that catalogs every known and potential site, monitors their preservation status in real time, and models the interactions between ancient societies and their environments on a global scale. This would not be a static map in a book, but an interactive platform, constantly updated with new data from drones, satellites, and ground surveys. It would allow us to ask questions we never could before, comparing the urban planning of the Khmer with the Maya on a systemic level, or tracing the global spread of agricultural innovations. The ultimate goal is no longer just to find what was lost, but to understand the full, interconnected story of humanity's journey across the Earth, written in the silent language of the landscape itself. The glowing map on the screen is only a hypothesis, a beautiful, intricate guess written in topographical data. To transform that digital promise into historical fact, the journey must return to the Earth. This is the indispensable human phase called ground truthing, where boots meet the soil and the virtual world is tested against tangible reality. It is a partnership that completes the circle, with the technology acting as the most precise treasure map ever drawn, and the archaeologist as the explorer who finally reaches the spot marked X. The true validation, and often the most thrilling discoveries, happen not in the sterile glow of a computer lab, but in the humid, buzzing heart of the jungle itself. Guided by the coordinates from a LiDAR survey, a field team will navigate through what appears to be impenetrable wilderness. To anyone without the map, it is just a wall of green, an endless tangle of vines and trees. But the team leader holds a tablet, and on it the forest has been digitally erased. They know that just 300 meters ahead, through that thicket, the land should rise into a wide, level platform. They know that to the left, a subtle linear ridge indicates an ancient roadway. With machetes and determination, they follow the digital breadcrumbs. After hours of arduous travel, they emerge into a clearing they would have never found by chance. The ground underfoot is unnaturally flat. The LiDAR model was correct. They begin to clear the leaf litter carefully, and their trowels soon scrape against not soil but the smooth, cut stone of a paved floor. They have found the plaza. The digital prediction is now a physical place, but the map cannot tell them when this plaza was built, who gathered here, or what purpose it served. That is where traditional archaeology takes the lead. The team sets up excavation units, digging in careful, measured layers. They sift the soil, searching for the material time capsules that hold the answers, fragments of pottery whose style can be dated, chips of obsidian from traded tools, or samples of charcoal perfect for radiocarbon dating. Each artifact pulled from the earth is a word added to the plaza's story. The pottery styles might place its main use in the 8th century. The arrangement of surrounding mounds suggests it was a public gathering space, not a royal residence. Perhaps they find a broken ceremonial incense burner, hinting at spiritual activities. This ground truthing does more than confirm the technology. It gives the digital ghost a body, a date, and a cultural context. The laser showed the shape, but the excavation reveals the soul. This collaborative dance between the satellite's eye and the archaeologist's trowel is where history is ultimately written, one verified, tangible piece at a time. The frontier has not disappeared, it has simply changed its form. The great age of geographical exploration, of sailing off the map into literal terra incognita, may be over, but a far more profound unknown has taken its place. Our new frontier is not a place but a layer. It is the hidden dimension of history that lies beneath our feet and within the data streams flowing from orbit. The blank spaces on our maps are gone, replaced by a world we thought we knew, now revealing itself to be filled with secrets we never suspected. This is the new age of exploration, and its pioneers are a unique fusion of data scientist, historian, and field researcher. Their vessel is not a wooden ship but a constellation of satellites. Their compass is not magnetic north but the predictive logic of an algorithm. Their treasure map is a point cloud of laser light, and their ultimate destination is a deeper understanding of our shared human story. This convergence makes the present moment one of the most electrifying periods for historical discovery in centuries. For the first time, we possess the tools to systematically interrogate the entire planet, to ask the land itself what happened here, and to receive an answer in the language of topography and spectral signatures. The adventure is no longer about finding a new continent, but about rediscovering the complexity of the world we already inhabit. It transforms every patch of forest, every desert plain, and even the ground beneath our modern cities into a potential site of revelation. The thrill of discovery is the same, but the scale and precision are utterly unprecedented. We are not just looking for lost cities, we are learning to see the invisible patterns of ancient life, to hear the echoes of societies in the way a river bends or a stand of trees grows. This is exploration turned inward, a journey back through time using the most advanced tools of the present, and it promises to rewrite our origin story with every new survey. This evidence forces us to confront a profound philosophical shift about our species. For generations, a powerful narrative held that the truly natural world was one untouched by human hands, a pristine wilderness existing apart from us. Our own industrial age, with its clear environmental costs, reinforced the idea that large-scale human modification was a modern and often destructive phenomenon. The maps from the jungle and the desert dismantle this idea completely. They reveal that the ancient world was already a deeply anthropogenic planet, a place where human ingenuity and the environment were in constant creative dialogue. These societies were not passive inhabitants of a static landscape. They were its architects. The vast networks of causeways, the sprawling grids of canals, and the geometric earthworks are not just ruins. They are testaments to a sophisticated form of ecological engineering practiced for millennia. The Maya did not simply live in the rainforest. They sculpted it into a productive, managed garden city. The Khmer did not just settle near water, they built a machine of earth and stone to command it. This long-term, landscape-scale thinking reveals a depth of environmental knowledge we are only beginning to appreciate. It suggests that sustainability is not a new concept, but an ancient challenge that past societies met with varying degrees of success. Some of these systems endured for centuries, a testament to their resilience and careful balance. Others, as we see in the eventual transformations of these civilizations, may have reached their limits, prompting adaptation and change. This history reframes our current environmental predicament. It shows that humans have always shaped their world for better and for worse. The question is no longer whether we will modify our planet, but how we will do so. The past offers a library of experiments in large-scale living, a record of both profound harmony and potential overreach. By studying these ancient blueprints, we are not just uncovering lost cities, we are rediscovering a forgotten chapter in humanity's long conversation with the Earth, a conversation about how to build a home that lasts. The story these maps tell is one of radical humility. For every city revealed, 1,000 questions are born, and with each new digital survey, decades of settled theory can dissolve overnight. This is the true power of LiDAR and satellite mapping. They are far more than sophisticated tools. They are active catalysts for a paradigm shift. They have transformed archaeology from a science of slow, localized excavation into a dynamic, global conversation with the past itself. We are no longer just reading history, we are engaged in a live, planetary-scale revision. The most staggering realization is how little we have actually seen. While the headlines celebrate lost cities found in Guatemala or Cambodia, the truth is that most of the Earth's land surface remains unexamined by these digital eyes. Vast stretches of the Amazon, the Congo Basin, the Asian steppe, and countless islands and coastlines have never been systematically scanned. We possess the technological capability to create a complete archaeological map of our planet, but we have only sketched the first, tantalizing corners. The map of human history is therefore profoundly unfinished, and every new flight, every new satellite pass, adds another piece to a puzzle we are only beginning to assemble. This ongoing revolution invites a new relationship with our past, one built on curiosity rather than certainty. It asks us to hold our assumptions lightly, knowing that the next breakthrough may come not from a dig but from a dataset. For anyone captivated by this story, the journey does not end when the video does. You can follow this unfolding discovery by supporting open science platforms and cultural heritage initiatives that make data accessible and protect vulnerable sites. You are living in the era when the greatest chapters of the human story are being rediscovered, written in the silent language of the land, and revealed one laser pulse at a time.